Thank you for coming to the SSA Canberra October branch meeting. My name is Nelson and I was the council coordinator for the Dennis Trewin Prize this year, which this branch meeting is dedicated towards. So to begin, in the spirit of reconciliation, the SSA acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Just a quick reminder that unless you're speaking, please ensure you mute your audio in order to minimize feedback. Video is entirely up to you as to whether you wish to leave it on or off. So today's meeting celebrates the achievements of two outstanding PhD students who have been jointly awarded the Dennis Trewin Prize, Ali Jaipur and Chen Li. As many of you will know, the Dennis Trewin Prize is awarded for outstanding postgraduate research in statistics and data science conducted in the ACT or regional New South Wales. Shortlisted candidates are required to submit a short video showcasing their research. I would like to give a big shout out to the selection panel that reviewed the video submissions for this year and made their deliberations, which consisted of Dennis Trewin himself, Belinda Baker, Janice Seeley, and Eric Stone. This evening, we are privileged to have Dennis join us as a special guest. The prize is named in honor of Dennis and his substantial contributions to the statistics community, both nationally and internationally. He is well known for his role as former Australian statistician and also as a recipient of the Officer of the Order of Australia. I would now like to invite Dennis to say a few more words about this year's prize.
Right. Well, thank you very much, and thank you all for joining a special seminar for the winner of the Dennis Trewin Prize for the best presentation from PhD studies. As you just heard, there are two joint winners. Winners this year are Ali Jaipur. I've got your name close to right. For his PhD at the University of New England, and Xian Li, who's studying for his PhD at ANU. I'd like to join everyone else in congratulating you both in jointly winning the award. Ali's presentation will be on the use of neural networks for the biometric identification of cattle using their muzzles. This work offers a promise of far more efficient methods for identifying cattle and clearly demonstrates the value the expertise of a statistician can add to solving real-life problems. Xian's presentation also tackles a practical problem. In his case, it is where practical computational problems to the analysis of a very big data set. He shows by the use of a series of subsamples, you can considerably improve the computational accuracy with relatively little loss of accuracy. I'm looking forward to hearing both presentations. And finally, I would like to thank the Canberra branch for naming this prize in my honour, especially when I'm still alive. I'd also like to acknowledge the contribution of my fellow judges, Belinda, Eric and Janice. Everyone's effort is really appreciated. Thank you.
Thanks for your reflections, Dennis. So just as a final shout out, the Canberra Council would also like to thank the SSA Central Branch for helping to sponsor this prize partly. So now without further ado, let's get into the presentations for this evening. Our first speaker will be Ali Jaipur from the University of New England, who is currently completing a PhD within the School of Science and Technology. Ali's talk will be about the advantages and existing barriers in the biometric identification of cattle. I'll hand over to you now, Ali.
Okay, hello everyone, and I'm glad to be here with you today, and thanks for introducing me, Nelson. I'm really honored and humbled to receive this award, and I appreciate the panel. So, as you know, today I want to talk about the cattle identification methods in general and check its advantages and disadvantages of the current methods, and also the existing challenges in this regard. You know, these days, livestock products are in high demand, and hence farmers trying to expand their herds and have more animals in their farms to receive more benefits from this market. So obviously, when they growing their herds, they need to do some they need some requirement and need to do some things like as identification. So particularly, I'm talking about the cattle identification in this presentation. And the first question arose what...
Ali, sorry, can you share your screen? I think you haven't shared your screen as yet.
Yeah, but I'm still not in here to show
Oh,
you.
sorry, apologies.
Yeah, no worries. As soon as I want to show you something, I will share it my screen as well.
Apologies.
Yeah, no worries. And so this question happened, why the cattle identification is important. It's really simple. You can simply answer it, first of all, because of their health. They can monitor, the farmer can monitor them, for example, what if individual cattle or particular cattle has some disease or problems, they can control them, and a special drug if needed, and if need to separate them from others, they can control them as well. And also try to check their family history, like generations and something like that through this. And the most important part is for monitoring them, because the cattle will be moved around the herd and farm. So I have a friend who has a farm, and he told me that sometimes my cattle will be moved to the neighbors' farms, and we try to distinguish them, especially the Angus breed, because the Angus breed are really popular in Australia. They are really all black and similar together, so they just put some paint on it to try to identify them through the neighbors' cattle and distinguish them. And also for managing their nutrition, also they need to identify their cattle. So this question happened next, what is the current method of identification for cattle identification? And for better understanding, I will show you some photos in this regard. And first of all, as you can see in this photo, this is the small cattle, baby cattle, and you can see they're using ear notching for identification, and two parts of this ear and this ear will be removed, and you can imagine it's really painful for animals. It's invasive method. And the next method some farmers use is freeze branding. As you can see, they just try to tattoo them, and it's still harmful and painful for animals. And the most common way for cattle identification in all around the world, especially in Australia, is through the ear tagging. And as you can see, the cattle has a ear attached to their as a tag attached to their ear, and it includes a specific number which belongs to that cattle. And yeah, it's as obviously it's completely determined. It's not a really good method for cattle identification. However, they are already using this kind of method. And beside the invasive and painful, these methods can be a cause of infection even in animals in a long term, and even in somehow can affect on the products. For example, if you are going for shopping, you can see some chicken or eggs on the shelves are defined as a free-range caged eggs and free-range eggs, or even in cages, and the price almost different. And this is because the freedom is really important for animals as well, for animal welfare. And on the other hand, with the development of the science, it's really necessary to improve our old methods, and we should do it as well. But in this way, it's in this way for cattle identification, we can say that we just try to identify the cattle by their images or videos, which is really touchless method, and it's not invasive and cannot or bad effect on animal welfare. Also, imaging-based methods are not too much expensive compared to the traditional methods, because for traditional methods, we need equipment, more people to do this, and but for the cattle identification, recently everyone has a mobile phone, and they can use that for capture the photos or doing this identification in future. However, we still have some challenges, barriers in this regard. And first of all, is we don't have a publicly available data set. It still has some researchers try to collect some data set in this regard, and I try to contact them to receive those data sets. Unfortunately, I couldn't receive any response from them. However, those data sets are in a small, using for small herds, like 10, 20, or 30 cattle. And because first of, when I decided to do this research, it was really important for me that the model and the method I want to apply can be used in practical settings in real environment. So I really need at that time to a big data set. And I try to contact some colleagues in my university, because we have a Tulimbo feedlot in University of New England, and we have animal science people here. So with help of them, I managed to collect some data set. But before that, let's have a quick look at these photos. For example, this one, you can see it's a Holstein breeds, and they are all has a different pattern on their body, coat pattern, and you can easily, through the computer-based method, you can distinguish them because they are identical, they are different in patterns. However, this breed will be used for milk products, something like that. But the most, but at the beginning, this question comes to my mind: is that possible that we prepare a model or method that can be used regardless of the breeds for any kind of cattle? For example, these cattle, these photos taken from Tulimbo feedlot, and you can see all these cattle looks identical, and they are all black, some similar together. And imagine a big herd like 1,000 of these cattle in a practical setting. So how we can identify them? So after some research, I noticed that the muzzle has a pattern, the cattle muzzle, something like the human fingerprint. As you can see, this is the muzzle pattern, and it's not related to a specific breed. All breeds, for example, this one is Angus, and this is another sample from Hereford breed, and you can see it still have a unique pattern, which is unique for each individual, like the human fingerprint. However, after contacting with my colleagues in animal science, through the induction days, I could arrange a time for data collection, and we managed to collect the data as 300 cattle. However, this was not an easy task. As you can see, each cattle comes to the something like a cage. They call it crush, and their head was then tried to be sealed with some device called head scoop to just adjust it and fix it, because they need to do just some injections and also put some eye treatment, tagging, or something like that. However, with this situation, these cattle, because you know that this is one of the another concern, another challenge in this way, the cattle are big animals and they are not really cooperative. So it's really hard to handle them. And by the way, with this situation, they still can move. And as you can see in these photos, this is the data set, the sample photos of the data set that I collected. And as you can see, in part A, this is the different breeds of cattle. This is normal photos we used for cattle identification, usable. And the part B is some blurry image, and some didn't capture the muzzle as well. And yeah, it's not suitable for detection. And however, in part C, because we used, I used the BROS mode for capturing the image. However, still the cattle could move his head, and you can see that, for example, in this image, we couldn't capture the muzzle properly and cannot be used. On the other hand, it was really important for me, as I told you, that I tried to implement a model that can be used in a practical setting. So it was really important for me that this model worked with less data. and for each individual, I mean, individual cattle. Because in a practical setting, you know, collecting a large amount of data is not really possible. We should do the detection and identification with just a few images. So I decided to prepare a model with working with less amount of images. And on the other hand, I try to use the latest methods, like mentioned before, using the deep learning, deep neural network, which you know that deep neural network, it needs this kind of networks and models needs large amount of data for each individual classes to work perfectly. Otherwise, the overfitting will happen. Overfitting means the model can learn the training data set, the data set would train, but the new data, the new classes like validation or test classes will come, the model could not achieve a good accuracy or couldn't work properly. So this was another challenge in my case, because I should do it with less amount of data. I try to do it with only 5 images per individual class, and totally, I told you, 300 cattle, 300 classes I have. And in this regard, also, it's worth mentioning that all previous methods or previous models or researcher, most of them try to extract the muzzle manually or just collect the muzzle data set, or some of them, for example, put some ink on the muzzle of the cattle and just put a paper on it and remove it and scan that image, that paper, which is not really effective. However, I try to do it automatically through the system. So in this regard, I'm using the YOLO network, which is working is a neural network, and the original image comes to the system. We try to resize the image, and through some methods which couldn't affect on the quality of the image. And after that, try to annotate the muzzle and train the YOLO network. That it is worth mentioning that the YOLO model was pre-trained on ImageNet, which I use the transfer learning, which I will describe it later more. And the best weight will be extracted, and then for testing phase, just the original image come to the model, trained model, and muzzle detected and extract. Once the muzzle extracted, then I try to use another CNN for identification. But before going to that one, let's have a look to these results. This is the YOLO results for detection part. And as you can see, I use different resolution as a network input network resolution. And once I increase the resolution, the validation, the test accuracy also increased as well. However, this is the nature of the YOLO V3, which means by expanding and increasing the network resolution, the input network resolution, the model can detect the small object as well, and the price it will be work better and can be achieve the better accuracy. And as you can see, it is obvious in our implementation that it works. But this question may come to your mind: why we don't continue this network resolution, for example, 2020, 3020, or something like that. But as you know, one of the important things in implementation of any CNN models is the model complexity. As soon as you increase the network resolution, the model complexity and taking time will be higher, and we don't want this. We want a quick model that can be used. And because in this situation, we achieve this accuracy with this network resolution, it doesn't have necessary to go further for other resolution as well. So in the next step, after I detected and extracted the muzzle, I just try to use another CNN for cattle identification. And in this regard, the muzzle dataset comes to the CNN model, which in this case, I use shallow networks because we have a limited image. They can be worked better, and extracted the ResNet 15, which I will explain it furthermore. We try to extract the features of those images, and with the classifier update the parameters. And once the model with best parameters obtained, then another model image come to the models and the feature extracted and classified, and then the prediction will be happen. Which according to this framework that you can see, I try to, as you can see in this figure, I try to use different settings to see how the models work. And first of all, I try to train the model from the scratch. And here, the blue line, you can see it's training from scratch without anything like transfer learning or something like that, which I explain it. And after about 19 epochs, it could achieve an accuracy of 90. But unfortunately, after that, immediately dropped, which overfitting happened. So to avoid this problem, first of all, we can stop the training procedure by somehow like here, and that models, a safe model can be used for prediction, but it's not really effective in CNN models. And also it takes a long time, and the accuracy 90 still can be, we can reach a higher than that. But the transfer learning, which means the model was pre-trained on another data set. In this case, it was ImageNet, which had 1,000 classes, include 1,000 classes. And we just remove the classifier and put ORT classifier inside it and train the model with just only 5 images, as I mentioned before. And after about 20, almost 15 to 20 epochs in transfer learning here, we reach the accuracy of more than 90%. And you can see the difference here between the training from scratch and transfer learning. However, we're just going further to see if we can improve our model performance. So by fine-tuning different layers, which the last layers, and fine-tuning 3 last convolutional layers, we managed to achieve the accuracy of 99 almost validation accuracy, I mean, after only about 10 epochs. So you can see that the difference between 10 epochs and 90 epochs from scratch. So with this job, we try to save the time, the model complexity. So the model no need to train for a long time, and the time was shorter, obviously, and the validation accuracy was really acceptable for me. After we achieve all these results, we realize that transfer learning and fine-tuning, it's really can be really useful for in our case. So I put another step, go further, and try to use different convolutional neural network, which means, as you can see in these tables, the 3 different models: ResNet 50, PGG 16, and MobileNet version 2. All these models are the shallowest network, and they are shallowest in their kinds. And because we have a less amount of data, this can be really helpful to select the appropriate CNN model. And as you can see, I just used 2 different parts: transfer learning and fine-tuning, because I said before, these methods was really helpful. And each CNN model has a different application in different environment they can be used. For example, ResNet 50 and VG16 can be used in a computer or in some cloud server. For big computational server can be done through that cloud, so they can be used in that place. And on the other hand, MobileNet version 2, which obviously through the name you can understand it is something related to the smartphone and can be used in a smartphone and trap camera or so on. So on the other hand, the size of them, you can see, is completely different. The MobileNet version 2 was much smaller compared to the VGG16 and the ResNet 50. So what it is worth mentioning that ResNet 15 achieved the highest accuracy in fine-tuning, 99.11 in testing phase, which from 563 images belong to 300 classes, 558 one classified correctly. but other also in fine-tuning of VG16 and mobile net version 2, they could achieve acceptable accuracy. Also, they are lower than the Resident 50, but still acceptable and can be used. So to prove this work, which I told you, it was really important for me that the model can be used in practical settings. So I tried to implement the mobile net version 2 in a real smartphone app. So in next step, I tried to implement the muzzle detection through the smartphone app, which through the TensorFlow Lite. And as you can see in this screenshot of the app, the muzzle can be detectable in single shot. 4 of different breeds of cattle can be detected with high accuracy, and after that can be extracted. And through another app, which still I'm working on it to develop it, to fix it, to make it better, you can see the identification happens with we use the show the inference time and something like that. So it is really important that we said, because first of all, I mentioned that it is possible to do the cattle identification, computer-based method for cattle identification in a practical setting and using a low amount of data per individual cattle, and tackle lots of problems and issues like overfitting and in this regard. However, at the end, it can be concluded that the computer-based cattle identification is possible in practical settings, but it still needs some more experiments and investigation to find most proper method. Because one of the drawback of the current method, because for example, in this photo, you can see one of the limitation of the current methods we realized. The muzzle is the part of the face of the animal, cattle, which used for eating something. And obviously, it can be anything stick to it, attached to it during the day, and because they are in a far. And to avoid this issue, first of all, we should remove something from their muzzle and then capture the photos like a human fingerprint. If you're going to some organization, they want to collect your fingerprint, they ask you to first clean your fingerprint if something stick to it or attached to it. However, we suggested that for future, because I told you at the beginning, it's really hard to try to be close to these kind of animals. They are really big. So it's really helpful if we can combine some methods to tackle this issue, to tackle these problems. And for example, face recognition identification combined with muzzle detection and identification, or body pattern as well, to achieve a better accuracy and proper model. However, with these implementations, I tried to achieve my goals, with which I was set at the beginning of my research. And however, I tried to take a little step in this regard, and hopefully something good happened soon, and some products and application produced in the near future in this regard. Okay, thank you for your attention. I'm here listening for any question if you have.
Thanks so much for that talk, Ali. Do we have any questions from the audience?
No, nothing, just I try to explain everything, and if anything, any question happen for audience, I will glad to answer them if possible for me.
Yep, so we have a question that's come in from Tao. So thanks for your interesting talk. Do you use a general data augmentation approach or a special one? So I think you're on mute, Ali.
Oh, sorry. Thank you, Nelson. First of all, thank you, Tao, for your questions. Actually, for data augmentations, because I told you it was really important to model work based on the low amount of data. So we just try to use some libraries in Keras and TensorFlow, based Keras and TensorFlow, to augment it, some image and produce some image during the system when we try to working. So it means it doesn't produce an actual image, but when the image come to the model for training, before that model try to in a different angle or different size, different angle or brightness or something like that, it try to do it automatically and then learn it. So all this happened through the library, not actual image using this regard.
Thank you. I think we also have a question from Brenda.
Hi. Thanks for the interesting talk, Ali. Yeah, so I'm interested in when you explain the result from different models. Can you elaborate a little bit more on that? So what are the differences between the models in terms of parameterizations? And also, can you also elaborate on the stochastic that involved in the model as well? So given the same image, will you have different outcome if you change the model setting and things?
Yeah. Thank you, Brenda, for your question. Actually, as I mentioned before, for different neural network, different models has different working tasks, and they have a different layers. Some of them is really huge and some of them is smaller. In this case, because we had a small amount per each individual cattle, so we try to use some shallow networks, which I mentioned, which is 16, Resident 15, and MobileNet version 2. The difference between them, according to its applications, they are working differently because they have a different layers inside it, and they working differently for extracting the features and try to learning the objects, the features of those images for training. However, as you can see, they could achieve the acceptable accuracy, and the parameters could learn, and the weights could update it through the backpropagation, very good, and the parameters updated according. But it's really important that we use transfer learning plus fine tuning, which is really important. Otherwise, the model can face with overfitting or other issues. And their applications, I mentioned, it's different in different settings. They can be used, some of them in cloud, because they need much more resources for working, much more resource for working properly, like VGG16. But on the other hand, the MobileNet version 2 is not need much resources, can be used in a smartphone. And obviously I can show you some screenshot as well from the apps. So yeah, they still have lots of models that can be used and can be investigated, but according to current research and in this regard, and because of the issues I told you before, I try to use these three models.
Thank you, Ali. One last question for me. How do you detect the overfitting from that model?
Pardon?
How did you detect the overfitting?
Once the overfitting happened, you mean about the overfitting, yeah?
Mm-hmm.
Yeah, once the overfitting happened, the model during the training, it can be because during the training we try to save the log, and through the log we can realize that this place the model overfitting happened, or maybe during the test you can notice that. But in that image I show you, when the model trained from scratch, it couldn't learn very fast and very good. But once we use the transfer learning along with fine tuning, means some of the layers, the beginning layers of that model was freeze, and the last convolutional layers according to some experiment, we tried it to defreeze it to learn more features, more important features of that image. And as you can saw, we achieved the good accuracy in this regard.
Thank you.
You're welcome.
Cool. Thanks, Ali. So I think we'll move on to our next talk. So the second speaker is Xian, who is completing a PhD in statistics at the ANU. Xian's talk will be on the topic of sub-bagging variable selection. So I'll hand over to you now.
Yeah, all right, yeah, thanks, Nelson. Yeah, firstly, I'd like to thank the committee to give me this precious opportunity to present my work. Yeah, and also secondly, I would like to give the thanks to two of my supervisors. So this one is a joint work. Without their patient support, help, and encouragement, this work cannot be finished. Yeah, so today's talk is about sub-bagging variable selection. And this one is the structure of today's talk. So I will firstly briefly introduction on the current literature and motivation of our work. And then I will introduce the method. And followed by that, I will introduce the theoretical result. And then followed by that is numerical analysis. And then I will draw a brief conclusion. Okay, so firstly, let's review the concept of bagging. So the concept bagging was developed to improve the prediction by combining prediction result of randomly generated training sets. So suppose this one is our original data set. And then by using the sampling with replacement, we can generate a bootstrapping sample, which has the same size as the original data set, right? Then we can make a prediction based on this new, newly generated bootstrapping sample. Then probably we are not only generating one bootstrapping sample, so we are generating several bootstrapping samples. So here I generate mn bootstrapping sample, and for each bootstrapping sample, we can make a prediction, right? And combining those results, you can either use simple average or other method to combining those prediction results. Then this one will give you the bagging method. So that's the reason it's called bagging. So it's bootstrapping sample aggregating. So why do we need to use bagging? So there are two advantages. The first advantage is that we can avoid overfitting. So it can improve our prediction. And the second advantage is that the computation can be performed in parallel. So because as you can see, if we make prediction based on each bootstrapping sample, and the computation of those predictions are independent to each other, so we can have the parallel computing. And some example of application is the first one is bagging trees, and second one is random forest. Yeah, so that's about the review of bagging. So probably if we are dealing with a really large data set, and it would be really hard to generate a bootstrapping sample for that original sample, right? So yeah, so instead of generating bootstrapping sample, probably we can generate a subsample from that really large original data set. So this one is like the original data set, and then we just generate a subsample. Because we are generating subsamples, so it doesn't necessarily for us to use the sampling with replacement. So here for better efficient sampling, here to generate the subsample, we use the sampling without replacement. Then based on this subsample, we can make some inference results. And still, by using the idea of the bagging, so instead of generating one subsample, here we generate mn subsamples, and for each subsample size is kn, and it's far less than the original data set. Okay, and for each subsample, we can make some inference results. And we can combine those inference results. Then it will give us sub-bagging method, which stands for the subsample aggregating. Yeah, so that's the idea of sub-bagging, which is an extension to bagging. So yeah, so those are the advantage of using sub-bagging. It can still avoid overfitting, and it can be performed in parallel. And most importantly, because we are using the subsample, and the subsample size is much smaller than the original data set, so it can help us to save memory. Because if you want to do any computation, you need to load the data into the memory. However, if we use the sub-bagging method, so we don't need to load the whole data into the memory. We can just load the subsample into the memory, so which saves memory, and it can be an alternative method to deal with big data problem. Yeah, so let's have a brief review on the current literature in sub-bagging. So the first aspect about sub-bagging is prediction. So and ANOVA just proved that the sub-bagging can also produce stable predictions. And Billman also proposed a method called sub-bragging. And the reason it's called sub-bragging is it involves some robust method to aggregate the prediction from subsamples. So that's the reason it's called sub-bragging. And most recently, it's our first project. So it's work from my supervisor and I. We work on the sub-bagging estimation. And we theoretically show that the sub-bagging estimator is a square root n consistent. So which means sub-bagging estimator enjoys the same converge rate as the full sample estimator. However, we find that there's an inflation rate in its asymptotic variance compared to the full sample variance. And the inflation rate is just 1 divided by alpha, and here alpha is defined as the kn, the subsample size, times the number of subsamples, then divided by the original data set. So I will explain this part later, because we also find that we have variance inflation in the sub-bagging variable selection, and I will explain that later. So yeah, so now the current literature, we have the sub-bagging prediction and sub-bagging estimation. So a natural question is to ask, can we have sub-bagging variable selection? The answer is yes. So currently there are some sub-bagging variable selection methods are proposed to combine the selected variable from different subsamples by majority rule or set intersection. So I just demonstrate that idea in this graph. So as you can see, from different subsamples, we would select different variables, right? And how to combining those variables is a problem. So say you see here in the first subsample, we select beta 1, beta 2, and beta 4. And in the second subsample, we select beta 1, beta 3, and beta 4. So they are different selected variables. So current method just use the majority rule or set intersection to combining those results. However, there are two problems with this method. The first problem is that such methods do not produce good and stable results. And the second problem is that it's really hard to establish the theoretical framework for those methods. So in our first project, because we're working on the sub-bagging estimation, so we in the first project, we just overcome the theoretical difficulty in the sub-bagging estimation. And this one can provide an alternative aspect for the variable selection. So one possible method is we just follow the spirit of adaptive lasso. So yeah, so let's have a brief review on the adaptive lasso. So because we are consider variable selection, and you will have a loss function, right? And you just penalize that loss function. And here, this one is just some tuning parameter, and here, this one is some weights. Then you just optimize this penalize the loss function, and you can have the variable selection. And now here comes to our method. So because we have mn subsamples, right? And for each subsample, we would have a loss function, and we just use this one to denote that loss function. And this one is just a subsample size, and this one is just the index of the subsamples. And the minimizer of this subsample loss function is denoted as this beta tilde. And this minimizer, beta tilde, can also be called as subsample estimator, right? Because it's the minimizer of the subsample loss. And we can further denote this one as the second derivative as the subsample estimator. Okay, now we have those notation. Then because we have the subsample loss function, right? So a natural way to aggregate those subsample loss function is just by simple average, right? And we can use the least square approximation to approximate that average. So this one is, I use this one to denote the simple average of the subsample loss function. And we use the least square approximation. And this one is the notation for the least square approximation to approximate this simple average. And this one is the definition of the least square approximation. Yeah, and for those who are not familiar with the least square approximation, so basically least square approximation is just a way apply the Taylor's expansion on this simple average, and we just use the dominating term in the Taylor's expansion as the approximation to that simple average. Okay, so now we have this least square approximation, and we can use this least square approximation as the loss function, and we just penalize this this least square approximation, and then we can have the sub-bagging variable selection. Yes, probably I have a little bit too much words here, so a little bit confusing. However, we have graph to demonstrate that idea more clearly. So this one is our original data set. And we just generate mn subsamples, and each subsample with the subsample size kn, which is far less than the original data size. And for each subsample, we only need to obtain the following quantities. The first one is subsample estimator, and the second quantity is the second derivative of the loss function at the subsample estimator. So for each subsample, we only need to obtain those the quantities in the green boxes. Then we can aggregate or combining those quantities from different subsample by using the least square approximation. Then we just penalize that least square approximation. Then we can have this objective function, and we just minimize this objective function. Then we can have the variable selection. So there are two advantages in this method. The first one is that we can save memory, because you can see that during the optimization, we only need the quantities in the green boxes, right? Which means after we're obtaining those quantities in the green boxes, then we don't need to keep the subsamples in the memory during the optimization part. So yeah, so we can overwrite the subsample in the memory after we're obtaining those quantities. So this method can save memory. And the second advantage of this method is that we have the parallel computing, because as you can see, those parts are independent to each other, right? Like in the computation. So parallel computation can be applied at this stage. Yeah, so that's the advantage of our method. So you probably wonder why we have to use the least square approximation. Why we can't use this simple average as the loss function directly and penalize this simple average. So yeah, I also use this graph to demonstrate the reason why we can't do that. So still we have these mn subsamples, and you have all the data in the subsample, and you have the loss function, and you can aggregate loss function just by simple average. And you just try to penalize this simple average, and you optimize this objective function, then you will find a problem. Say if we are using like Newton-Raphson update, and for each update, you need to update the loss function. And if you want to update the loss function here, and you need to update the subsample loss function at each subsample, and which means you need all the data in the subsample. So this represents that during the optimization, you need to keep all the data in the subsample. You cannot overwrite those data during the optimization. So which means this method is not saving memory. And the second reason why we can't use simple average directly is that if we want to apply the parallel computing, it has to happen at this stage. But at this stage, we don't have any quantities to compute. So we can't not use the parallel computing. So that's the second problem with directly using the simple average. Okay, so yeah, so that's our methods. Now I will introduce our theoretical findings for our method. So yeah, so we assume that the true parameter vector will be a sparse vector, right? Because we want to do the variable selection. And under some conditions, and also we further assume this condition. So this n is the original data set, like the size of the original data set. And this kn is the size of the subsample, right? And we assume that this part will, this ratio will goes to 0. So the intuitive reason we have this condition is that because there are some bias in the estimate, and the bias won't disappear with the number of subsample we have, won't disappear with mn. So it only disappear when we have a large enough subsample size. So that's the reason we have this condition. And also we have the following conditions is the n goes to infinity, kn goes to infinity, mn goes to infinity. And we assume that this ratio, the subsample size times the number of subsamples we have divided by the original data set, this one will goes to a constant alpha. And we can have the following theorem. So the first theorem is about the estimation consistency. Yeah, so here's a mathematical notation. So basically the interpretation for this theorem is that we just show that the sub-bagging estimator is the square root n consistent estimator. So it's just imply that the sub-bagging estimator have the same converge rate as the full sample estimator. So yeah, so that's the interpretation for our first theorem. And the second theorem is about selection consistency, still under the similar conditions. We have this theorem. Yeah, still a lot of mathematical notation. But however, the interpretation for this theorem is quite straightforward. So it just means that the probability that we will remove any unimportant variable from our model converges to 1. And this just implies that if we can recover the true sparsity pattern if the tuning parameter lambda is properly chosen. Yeah, so that's about our second theorem. And now comes to our third theorem. So third theorem is called the oracle property. So basically, this theorem just shows a asymptotic normality holds for our non-zero estimator. Because we are doing variable selection, so there are some estimate at 0. So this asymptotic normality only holds for the non-zero estimate. And yeah, so we can show that for non-zero estimates, it still follows a normal distribution. However, we find that there's a variance inflation. So suppose this one is the asymptotic variance for the full sample estimator, and this one is the sandwich matrix for the full sample estimator. And in front of that sandwich matrix, we have this variance inflation. So yeah, so that's our finding, our interesting finding in the sub-bagging estimator. We find the variance is larger, we have variance inflation. And I have one more comment about why we have such variance inflation. So the intuitive reason why we have such a variance inflation is that the subsamples are not disjoint; they are overlapping. So yeah, so I just demonstrate the reason in this graph. So suppose this one is our original data set, and we only have this one blue observation in the original data set. And because we are using the sampling without replacement, so for each subsample, you can only have this blue observation shows once at most. However, because we are having several subsamples, we are having mn subsamples, so this blue observation can show in different subsamples. So which means the subsample are not disjoint, so they are overlapping. So that's the reason why we have such variance inflation. Okay, so that's about our theorem. Now we need to consider how can we choose the tuning parameter lambda consistently. So we just motivated by those two papers, and we just develop a BIC type criteria that can choose proper lambda consistently. So let's have a brief review on the BIC type criteria. So suppose we want to choose the lambda for the ordinary like full sample adaptive lasso. And in the classic settings, the BIC type criteria will be in this format. So we have two components. So the first component is the goodness of fit, and the second component is the simplicity of the model. So basically, the BIC type criteria just find a balance between the goodness fit and the balance, the simplicity of the model. So the lambda that can minimize this BIC will be the lambda can recover the true sparsity pattern consistently. So in the classic setting, we use the loss function as the goodness fit directly. However, in our setting, because we use the least square approximation as the loss function, right? And if we use this least square approximation as the goodness of fit directly, we can show that this one doesn't work. We can mathematically show that this one doesn't work. So still, the intuitive reason why this one is not working is that because we have the variance inflation for our method. So our variance is larger. So that's the reason this one doesn't work. So to make the BIC type criteria works, so and to consistently recover the sparsity pattern, we just propose the following like BIC type criteria, called as the sub-bagging BIC. So instead of using this least square approximation as the goodness of fit directly, so we need to have this scaling coefficient, and this Kn is just the size of the subsample, right? So we have this, so instead of using least square approximation as the goodness fit directly, so we just scale that by 1 divided by square root of Kn. And the simplicity of the model still stays the same. Then we can have this sub-bagging BIC. And now we just develop a theorem for this sub-bagging BIC. Yes, there's a lot of like notation here. So basically this notation is that some lambda can choose the like underfitting model, some lambda choose underfitting model, and some lambda can choose the true sparse model. So yeah, so we have this theorem. So although I have a lot of like notations here, but however, the interpretation for this theorem is quite like straightforward. It's just mean that the sub-bagging BIC we propose works. So suppose that we call that the lambda that can recover the true sparsity pattern as the proper lambda. Otherwise, we call them improper lambda. So it just means that the sub-bagging BIC with improper lambda will be greater than the sub-bagging BIC with proper lambda with high probability. So which means that the lambda that minimizes our proposed sub-bagging BIC can recover the true model. Yeah, so that's the interpretation for this theorem. Yeah, so that's all our theoretical results, and all our theoretical results are confirmed by the simulation. So this one is the settings of our simulation. So basically, we just follow Fan and Lee's paper. So this is the SCAD paper. Yeah, I think it's quite famous in the variable selection. So we just follow their setting. Yeah, and that's our first result. And here we only report the result for the non-zero estimates. So I already colored all the interesting findings in this result. So this one is the standard deviation of our non-zero estimate based over 1,000 simulation, right? So that's the standard deviation of the sub-bagging estimator. And this one is the asymptotic standard deviation for the full sample estimator. So as you can see, those results are quite different, right? They are not even close. However, as I say in our theorem, we find that there's a variance inflation, and we can use this ASD to times this 1 + 1 divided by alpha, which is the variance inflation rate, and we can obtain this alpha adjusted asymptotic standard deviation. And in this case, you will find that those values are close, are numerically close. So which means our theorem for the variance inflation is correct. And also because we not only derive the variance, the asymptotic variance, we also derive the asymptotic distribution, and we know that they are normally distributed. So we can also construct the confidence interval by using this alpha adjusted ASD, right? And we just construct a 95% confidence interval, and the coverage probability for those confidence interval should be approximately 95%, right? Because it's 95% confidence interval. And as you can see here, so the coverage probability for those confidence interval are approximately 95%. So which means our theorem for the sub-bagging estimator are correct. And here's our second result. So because we propose a new sub-bagging BSE, right? So we want to compare our proposed sub-bagging BSE with the classic BSE. So here we report the interesting finding is the false positive rate. So as you can see, if we use the classic BSE, which means if we use the least square approximation as a Gounod's fit directly, and this BSE cannot produce non-zero false positive rate. However, by using our proposed sub-bagging BSE or modified BSE, I just skew that least square approximation, then use the skewed least square approximation as Gounod's fit, and we can show that we can produce 0. So which means our sub-bagging BSE theorem works. Okay, so now here's the real data analysis. So I just be quick. So here's the real data analysis. We just use the US public use microdata area, and this data just include all the individual census information. And we just we want to make prediction on the income. And however, we have 24 covariates, and not all the covariates are related to this income, right? So we want to do a linear regression, and we want to do a variable selection for this linear regression. So that's our results. So we also conduct the adaptive lasso, the full sample adaptive lasso, and we compare that result with our proposed sub-bagging variable selection method. So as you can see, those are the results for the non-zero estimates. And for all the non-zero estimates, those methods just produce numerically close results. However, in terms of the standard error, we have like larger standard error. And also we compare the computation as well, because we say that we can apply the parallel computing and we can also save memory. So if we conduct the full sample adaptive lasso, and that's the memory we're going to use. However, by using our method, because we only draw a subsample instead of using the full sample, so we can save memory. And also in terms of the computation time, as you can see, the loading time and the estimation time is much less than the full sample adaptive lasso. Yeah, so that's our numerical results. Then let me have a brief conclusion to the contribution of this work. So in this work, we proposed a sub-bagging method for the variable selection and as well as a modified BSE type criteria for the tuning parameter. So the advantage of our method is that our method can save memory, so which means it can solve the memory constraint problem. And the second is that we can use the parallel computing, so our method is quite efficient, and also we can like avoid overfitting. So in terms of the theoretical contribution in this work, we just show that the sub-bagging estimates are square root inconsistent, which means it has the same convert rate as the full sample estimator. And the second theoretical contribution is that we can show that our method can select the non-zero variable consistently. And third theoretical contribution is that we derive the asymptotic normality for all the non-zero estimates, and we find that there's a variance inflation, and here is the variance inflation rate. And the last theoretical contribution is that we have shown that the classic BSE type criteria doesn't work for our method because our method is with greater variance. So we just propose a modified BSE type criteria, which needs to be modified by scaling the Green's feet. So yeah, so that's all my talk. Yeah, thanks for your time.
Ooh, thanks so much for your presentation, Tian. Do we have any questions from the audience? All right, I have a question. So your asymptotic results seem to require that k sub n grows faster than root n.
Sorry. You mean like the converge rate, right? You mean like the converge rate is greater than the square root of kn, all right?
The kn parameter itself. If you go forward, yeah. So if just go back to the slide. It says we assume root n over kn approaches 0.
Yeah. So
yeah.
Yeah, because we are not only using one subsample, so yeah, it's greater than the square root of kn.
Yeah.
Yeah.
Can you hear me?
Yeah, yeah.
So I think Nelson asked, you assume square root of n over kn goes to 0, right?
Oh yeah, yeah. That's the assumption. Yeah. 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 So sorry. Yeah. Yeah. So that's the assumption is about like so intuitively this one is about the bias, because bias won't disappear if you just increase the number of subsamples. So yeah, so we have some requirement on the size of subsample to make sure that the bias can disappear.
Jian, I have another question. Your subsamples for bagging were, I think, all simple random samples. Would there ever be a reason to consider some more complex sampling method, like do stratified sampling or something, to try to make each of those individual samples perform a bit better?
Yeah, it is possible. Like if we have like some information about those data, then probably we can try different sampling method. Yeah, to be more efficient.
Thanks.
All right. Yeah, thanks for the presentation, Tian. So that about does it for this evening. Yeah, thanks again to both Ali and Tian for presenting their innovative research with us. Also, thank you to Dennis for sharing his thoughts on the prize, and also thank you to everyone for coming along. So to wrap things up, I would just like to invite our interim president, Francis, to say a few words.
Yeah, thanks, Nelson. I should say also a very big shout out to Nelson for doing an outstanding job over the entire year for coordinating the Dennis Trewin Prize. He's done an amazing job and kept all of us on our toes, but also kept everything running very efficiently. So much appreciated to Nelson for doing so. I guess the only other two comments I want to mention are just up ahead in terms of sort of a couple of events to round out the year. We've got a workshop on advanced data visualization, which you can go to the StatSol website to find out more about. That's occurring on the 8th and the 9th of December. And also our NIBS lecture, which is occurring hopefully on the 30th of November. And we hope to have Professor David Steele from University of Wollongong presenting. And David is quite well known certainly in the Canberra community. So that's just a sort of I guess a heads up, a couple of events moving ahead. But other than that, again, congratulations to Ali and Xian for two very outstanding research projects. And thank you everyone for coming this evening.